All right, welcome back. Let's take a look at page 2, problems number what I guess is 5 through 11. Let's get going here. Okay, so first off, we say we've got a figure here that is supposed to be a rectangle. Now, one of the things that we've noticed is that some of you guys are not drawing your figures appropriately. So if you draw yourself a nice little rectangle here, and it's supposed to be labeled D, E, F, G. And so the place you start doesn't really matter, but the progression of the letters does. If D is right here, then E is the next letter. It's going to have to be one of these two places. So you could do D, E, F, G, but it has to literally go in order. And that's actually something that we've had. Some people have done a zigzag pattern. It actually is supposed to be directly in order, either clockwise or counterclockwise. Now, the interesting thing about this problem is it tells me something about DF. Well, DF then is not a side of the figure, it is a diagonal of the figure. So they're saying that portion right here, DF, is 5x plus 15. And they also give me that GE, which happens to be the other diagonal of the figure right here, that one is 8x minus 18. Well, that's pretty important because one of the features that we should know is that in a rectangle, the diagonals are actually congruent. Now, that doesn't happen in parallelograms in general, but in rectangles and therefore squares, it does. So we're going to go ahead and say that 5x plus 15 is going to be equal to 8x minus 18. Move the camera over a little bit. And so if we were to subtract 5x, we could say that 3x minus 18 is 15. We could add 18 to both sides, as we've done many times. I mean, just this kind of quick stuff that we do, those cancel. So 15 and 18 make 33. And I found x is 11. Awesome. So we're done, right? But let's double check. It says draw the given figure, solve for x, and then the length of GE. So I'm supposed to plug it back in. So GE, remember, was 8x minus 18, but we found out that x was 11. So that would be 88 minus 18, which is, I guess, 70. So the measure of segment GE would be 70 units. Cool. All right. Now, in a new rectangle, ABCD, it says the measure of the angle. Well, in this case, I mean, we could draw the figure, but we really don't need the figure because as soon as you have a rectangle, we should know that the measure of every angle is 90 degrees. So we're just going to go 2x minus 26 equals 90 degrees. We'll add 26. That tells me that 2x is 116. And therefore x would be 58. And it says find x, but it does say draw the figure, so I guess we will draw the figure. But here is A, B, C, D. Remember we said go clockwise or counterclockwise. Every one of these angles is 90 degrees. So of course, we can just do that. Now, number 7 and 8 are just questions about, do you know some facts about these stories? So a quadrilateral where opposite sides are congruent. Now, if it helps, you can draw a couple, like here's a kite. Well, if you look at it, A, B, C, D is a kite. CD is opposite AB. Those are definitely not congruent. AB is opposite CD. They're across from each other. Those are definitely not going to be the same. But a rhombus would be because not only are opposite sides congruent, all of the sides are congruent. So that is for sure. And same thing for a square. A square is all the sides are the same with 90. So those are pretty quick. Now, as it turns out, that's a fact that we learned for parallelograms, and therefore, one thing you want to remember is that a rectangle is a special parallelogram. A square is, so is a rhombus. All of those things are parallelograms. So if it's true for parallelograms, it must be true for all of those values. Now, for number 8, that's a little harder. When do you have a situation where the diagonals must bisect each other? Well, again, the diagonals bisect each other in all parallelograms. So that automatically is going to make it true for all of these, because remember we said that all of these things are in fact parallelograms. So those diagonals do bisect each other. But we don't necessarily know about trapezoids or kites, right? But if we drew a trapezoid like this, and we drew this guy in and this guy in, well, when I look at this, does this part of this diagonal look the same as this part? Well, I would definitely say that does not appear to be the case. And I drew a kite just a minute ago, but when I draw this and I draw this diagonal got bisected, but that one did not. So it turns out the answers for 7 and 8 are the same answer. All right, number 9. This is called the mid segment. Anytime you have a trapezoid that connects the midpoint of both sides, that's called the mid segment. Now, there's two really good ways to do this problem. The first one is you take the sum of the two bases and divide it by 2, and that should give you the length of your mid-segment. That's the formula. You're supposed to take base 1 plus base 2 divided by 2. It's supposed to be the average. And if we do a quick, cross multiply both sides by 2, we'd get 44. And therefore, x is going to be, let's see, we'll subtract 16 from both sides. And that's going to give me, I believe it's 28. Let me grab a calculator real quick and make sure I haven't done something silly there. 44 minus 16 is 28. Now, that's a great way to do the problem, but I actually noticed something else. If that number is the mid-segment and it is the average, an average has to be perfectly in between two numbers. And what I notice is to go from 16 to 22, I had to go up exactly 6 units. So if this is going to be smack dab in the middle, I could just go up 6 more units, and you'll notice that that gives me the number 28. So logically, you can actually figure that out without utilizing a formula. And number 10, our last one, is talking about whether or not these shapes are in fact similar. So there's a bunch of ways that we could do similar. One of them is if we could know two angles of any two figures. And that is actually true over here. I could say that is similar by A. You know, if you notice, they're actually marked. You could use similarity by SAS if you have one set of congruent angles and proportional sides, or you get triple S. Now, as it turns out, triple S was really the one we were shooting for here, but they actually marked some angles as well, so we could have gotten away with it either way. But we'll take a look anyway. So let's just see. Let's find out, is this one in fact SAS? That, I don't know. I mean, it's set up to be that way, but is it possible that the proportion is set up incorrectly? So here's what I'm going to do. I want to find out, is the proportion of 60 to 72, is the short side to the long side in this one the same as the short side to the long side in this one? And well, one of the things that I notice is, and of course you can cross multiply if you want to check that proportionality to find out if it is true. But I actually like something a little bit better. I'm going to divide these both by 11. And 55 divided by 11 is 5. And 66 divided by 11 is 6. And so I want to find out, is this one also 5, 6? And so I could look at how to reduce that fraction. And I happen to know that 12 goes into 60 exactly 5 times, and 12 goes into 72 6 times. But let's say you didn't know that, because again, not everybody's going to know all those multiples of 12. What you could do is you could hit 60, fraction key 72, and hit enter. And my calculator is designed to reduce fractions very nicely. So I definitely say that they are similar. It is a yes, they are similar by SAS, because the sides are in fact proportional, and there is that angle in the middle that is true. Now, the scale factor is interesting. Now, if you read the directions, it says, for each of the following, determine if they're similar. If so, state it, and then what's the scale factor? Now, what's missing from the directions that we just kind of, I don't know, it got missed, is we decided to make this one the pre-image and this one the image. This is the start, this is the finish. So what you're supposed to do to find the scale factor is put the new figure on top, put the old figure on the bottom, and I think I'm going to use 55 over 60. Again, as long as I take two corresponding sides and find their proportion, I just noticed that 5 goes into that 11 times and 5 goes into that 12 times. And like I said, if you didn't know that, we could do 55/60ths and get 11/12. Or you could do 11/12 and say the scale factor. You could say 11/12, or you could say 0.916. So in other words, that new figure is about 92% the size of the original figure. It got scaled down. Now over here, I really wanted to consider the side. Now I know the answer is going to be yes. We just found a really nice diagram and it happened to have more info than we really needed. So this is what I'd like to see you do, is I'm going to take the shortest side of this one and compare it to the shortest side of that one. Then I'm going to take the middle length side of this one and compare it to the middle length side of this one right here, which I guess would be 21. And then let's take the longest side of each and find out if in fact these proportions hold true. And I notice that these are both divisible by 6, which would give me 2/3. That's what that one is. 14 and 21 are divisible by 7, which gives me 2/3. And 16 over 24 is divisible by 8, which also gives me 2/3. Now again, 16 over 24, what you'll notice is it says 2/3. So all of these things are proportional. So I could use side, side. And then all I would have to do to talk about how that works is take any two sides that correspond with each other. So I'm going to go ahead and use the longest one of both because I just kind of like that. And I'm just going to say then that my scale factor is the ratio of the second one, which is the 24, over the first one, which is 16. And if I divide them both by 8, I get a scale factor of 3:2 or 1.5. So the new one is 1.5 times as big as the old one. And so that would allow me to take any side and figure something out about it. Okay? I will see you back in class. Good luck. Hopefully that was helpful.